Now, in the first part of the lecture, we saw that there is a membrane potential across the membrane. Now, knowing that the inside and also the outside contains ions, we would expect that there will be a pile-up at the membrane of these ions. This is what we would like to investigate further in the second part of this lecture. Now, here you see a sketch of the situation. So we have a membrane which is separating the inside and the outside of the cell, and we know there is a membrane potential delta V between inside and outside. Now, this membrane potential will lead to a pile-up of the potassium ions outside of the membrane and a depletion of the chlorine atoms at the outside of the membrane, whereas on the inside it's exactly reversed, where the chlorine atoms add up and pile up and the potassium ions deplete. Now, the question that we are asking now is, this charge build-up that we see here, how does this lead to actually the voltage drop, and how can we describe in more detail the voltage drop of delta V across the membrane? Now, the solution to this problem is basically looking into the electrostatics of the system. So the electrostatics of the system says that we have a concentration of ions outside, and the membrane we just view as a charge density on a flat surface. Then Gauss' laws tells us that the gradient in the electric field is equal to the current density, or the density of ions, rho of x, divided by the permittivity of the sample, which is epsilon times epsilon 0. Using this, we can obtain an expression for the voltage. Since we know that the electric field is nothing else like the gradient of the voltage, we rewrite Gauss' law in terms of the voltage, leading to the second derivative of the voltage with respect to space is equal to minus rho of the concentration of ions divided by epsilon epsilon 0, which is equal to the electric charge E divided by epsilon epsilon 0 times the concentration difference between positive and negative charges C plus and C minus at position C. Hence, analogous to the first part of today's lecture, again, if we know the concentration at any given place, we can determine the voltage at that particular spot. Now, for the concentration dependence, we now assume or make a certain ansatz, which is based on statistical physics, saying that the concentration of the ion at a given place is equal to the concentration in solution very far away, C infinity, times e to the power plus or minus, depending on positive or negative charges, E times the voltage at that place divided by kVt. So we think that if there is a voltage applied, well, positive or negative charges will be attracted or repelled from that place. By further introducing a reduced potential V hat, which is again the energy of an electron in the potential V in relation to the thermal energy. So V hat is equal to E times V divided by kVt. We rewrite the above equation into second order differential equation in in this reduced potential. So the second derivative of the potential with respect to x is equal to 1/2 times 1 divided by lambda d squared times e to the power minus b hat minus e to the power plus b hat, or which is equal to 1 divided by lambda d squared sine hyperbolic of the potential, where the lambda d is a summary of all the units, and in our case this is 2 times e squared divided by epsilon 0 kBt times the concentration of the ions at infinity. This is called the Debye length, which describes the length scale at which the potential will drop off to 0. So the differential equation that we just derived is the so-called Poisson-Boltzmann equation. Now the Poisson-Boltzmann equation for that particular configuration actually can be solved in an analytical way and will lead to some elliptical function, which is a fairly complicated function in terms of the reduced potential v of x, which I display right over here. The potential is dependent on various parameters. First is the Debye length, which, what you see above, is determined by the concentration of the ions in the solution. The second is another length scale, which is called the Behrung length, that relates the energy in the electric charge, so the energy between two electric charges, which amounts to e squared divided by 4 pi epsilon 0, and the energy involved in the thermal motion. Hence the Behrung length is just a fixed length scale, and it's the distance at which e squared divided by epsilon 0 times 1 over r is equal to kBt. Now the Behrung length is 0.1 nanometer. Now again, it's good to look on the Debye length, and what we saw is that the Debye length depends on the external or on the concentrations of the ions. Typically in cells we have 100 millimolar ions, and the Debye length is as small as 1 nanometer, so very comparable to the Behrung length. Whereas if you go to very low ion concentrations, so if we go to, for example, deionized water, where the concentration of ions is certainly below 100 micromolar, the Debye length can go up to a micron. Hence, any charges on a given surface will be visible even at a distance of 1 micron. Now, the very complicated solution to the membrane potential, or on the voltage drop, it's handy to look at a solution where the distance from the surface is much larger than the Debye length. So in that case, the log of 1 plus x divided by 1 minus x can be interchanged to 2 times x. And then we see that the voltage drop is actually exponentially dependent on the distance, with a typical length scale of the Debye length. In this graph, I've plotted the solution to the Poisson-Boltzmann equation for various values of the parameter x star, which describes the amount of charges that are on the surface in relation to the concentration of the ions outside. So if we have a very small amount of charges on the surface and the concentration of the ions on the outside is high, so x star divided by lambda debye approaches 0, and we see a steep rise in the concentration. And we also see that the drop off of the potential is very rapid in an exponential way. Okay, so let's wrap up what we learned in today's lecture. So we looked back again into some details on the electric potential that builds up across the membrane, and we came about the Goldman equation that tells us the membrane potential as a function of the concentrations of the different ions, potassium, sodium and chlorine, inside and outside of the cell. The Goldman equation faithfully predicts the membrane potential of minus 60 millivolt, which we can translate into an electric field across the membrane, which is only 5 nanometer thick, of 120 kilovolt per centimeter. Then we looked on the ion concentrations close to the membrane, and we saw that there is a pile-up of ions right or very close to the membrane, and the thickness of this double layer of ions is dictated by the debye length, which scales with the concentration of the outside ions or the ions in the solution. Typical length scales for physiological relevant situations, which is in the order of 100 millimolar, is in the order of a nanometer.